All right, so let's go ahead and get started. We're right at 10:15 on the dot, so we'll get moving along. I would like to thank everybody for coming to the session today for a couple of reasons. One, it's the third day of Build, so I know folks are a little tired. It's still early in the morning. We had the good fortune of not having the 8:30 session, which people are either really, really motivated to be at those sessions or they're still here from the night before. The second thing is I'd like to thank you for coming to this session because I also know there's a lot of other great sessions that are happening right now. So I'm very humbled that you have come to this one. So what we're going to be talking about today is what's new with Azure Machine Learning. Before I get into the talk, I'd love to do a quick survey, show of hands in the room. How many folks are using Azure Machine Learning today? Okay, awesome, thank you. How many folks have gone to a session this week that talked about Azure Machine Learning? Okay, basically the whole room. That's cool to see. All right, a couple other demographic questions. How many people are Python preference? R? C#? Scala? There's one up front. Julia? Okay, we've reached the long tail. So, all right, so let's go ahead and get into this. What I'd love to do is for the set of folks in the room who aren't familiar with Azure Machine Learning, I'm going to spend just a little bit of time talking about what we're up to, the problems we're trying to solve with the service. I'm really, really excited to have some great friends and customers here from ASOS. They're going to talk about how they're using Azure Machine Learning today to solve some pretty interesting problems. And then we'll go from that into what's new, what are some of the new capabilities, and then what's coming next. And so I'm really excited to be here. The team's really excited to talk about everything that we've been working on really, really hard. And so they also thank you for coming to this session. So let's first chat a little bit about the different pieces and parts of the AI capabilities that are in Azure. It's day 3, so you might have noticed we're talking about AI a little bit at this conference. And how we think about the world is really in terms of a set of infrastructure-based capabilities that you can use. We're building our cloud from the hardware up to be accelerated for artificial intelligence workloads. And that starts with what chips we put in all of the machines. Mark Rusinovich is doing a really interesting talk right now during this time. I'd encourage you to go check that talk out as well, where he'll dive into what we're actually doing in the data centers. Then on top of that, we have different compute and data infrastructures that you can leverage, because we know customers have lots of different kinds of data. It's different shapes, it's different sizes, it's stored in different systems. And there is no AI without data. And so that's critically important. And then we have a set of compute engines that really meet lots of different needs, depending upon what you're trying to do. If you have a data-intensive workload, Azure is the best cloud to run Spark in with Azure Databricks. If you want to scale out on top of a ton of GPUs, you just want to grab those and get running with those, you can use our Batch AI service. Alex Sutton talked about the Batch AI service earlier this week and about some of the really large-scale GPU-based deep learning workloads that we're running inside of Azure. In addition to the infrastructure, we have tools. And tools and frameworks are critically important. One of the principles of what we're doing inside of Azure is that fundamentally we are open to you using the tools and frameworks of your choice. We would be pretty silly if we did this presentation and said, hey, we've got a lot of really interesting machine learning stuff, but you can only use just one framework. We have customers that are using every framework you can name, and the next time we meet, there will be 2 more frameworks they're using that we've never heard of before. That's just the pace of what's happening in the ecosystem. And it's a feature of our platform that you can get this productivity with any framework or tool of your choice. Then we get into the services. We really divide the AI services up into 3 different categories. Conversational AI. This is about putting text and speech-based bots into your applications. We've talked about those a bunch this week. That's all I'm going to say there. The next is a set of pre-trained AI capabilities. And this is where we at Microsoft have done the hard work around getting the data, building the models, deploying the models, and all you have to do is make an HTTP request and you can put those into your apps. You can even customize some of those. You can take your own images and build a classifier on top of those. You can take your own examples of speech in order to create a speech engine that's optimized around your the words and vocabulary that are familiar in the setting that you're trying to optimize for. And then you always need the ability to go beyond that. And this is where the custom AI services come in. And this is what we're doing with Azure ML, which is really about when you want the most control and flexibility, the ability to pick and choose the framework that you want to use. This is the tool of choice for that. When we think about what it means to build a model, we really think of 3 stages to this. The first, again, there is no AI without data. So the first part of any one of these projects, and you'll hear ASOS talk about this as well, is about getting the data. And then it's about understanding the data, shaping the data, cleaning it, getting it into the right size and shape for you to then use inside of your next phase, which is building and training the model. Building and training the model is somewhat like software development, but it's a lot more iterative. You really end up exploring a lot of different ways, tools and techniques, configurations, in order to find the models that are going to perform the best. And then once you have that model that performs really well, you get into the last phase, which is I want to deploy this. This is where I actually want to go and deploy this into the cloud, deploy it to the edge. I want to put it inside of a mobile application that I'm building. This is where I actually want to use the model. What we're not showing on this diagram is that there's one more piece of this, which is once you deploy the model, it's super interesting to understand how is that model actually doing. So there's actually a stream of telemetry that's going to come off of the model that's going to go right back into the system. And that's critically important because customers' behavior is going to change, the types of data they use are going to change, and so you want to be able to update this as quickly as possible. So what is Azure Machine Learning? Azure Machine Learning is our platform. It's fully managed for custom AI development. We're really trying to solve 4 problems. The first is we want you to be able to build, train, deploy, and manage those models across any data at any scale. We don't want you to not be able to use the service because you need thousands of cores in order to train. But we also want you to be able to start just on your machine, train a model there, and then be able to deploy it. The second thing that we want to do is we want to be able to boost developer productivity with agile development. And this is, when you look at successful organizations, and ASOS will talk about this as well, it's incredibly important to reduce the latency of the time you have an idea to when you can deploy that model to when you can see how it is performing in the real world. And the more we can do in order to shorten that cycle, to make that loop go faster, the more productive you're going to be and the more creative that you're going to be. This is the secret sauce to really unlocking the flywheel of an organization that's going to take advantage of machine learning. This next one about being able to deploy these models everywhere is also critically important to our customers. Our customers don't just want to deploy into the cloud, although a lot of them choose to. They may need to deploy on-premise. They may have highly sensitive data that they can only score inside their own data center, and they want to be able to deploy a model there. They may have concerns around latency. They may need to be able to deploy to a remote facility that can withstand a loss of internet connectivity. And then finally, what we've been talking about a lot, and we showed a number of these things earlier this week, is being able to deploy to edge devices. And this is where you want to take the model and you want to put it as close to the event as possible. So I want to be able to take a model and deploy it on camera. I want to be able to deploy it onto a sensor that's on a tractor. And the reason I do that is so that I can make that decision as quickly as possible, as close to the event as possible. This last one I already chatted about, but this is about being open to the tools and platforms that you are using today. And our story with Azure Machine Learning is that if it runs on Python, which is almost the entirety of the ecosystem, you can go ahead and use it here. And we'll be adding other things as we go forward. There are 2 major buckets to Azure Machine Learning: the experimentation capabilities as well as the model management capabilities. The experimentation capabilities are all about that build and train phase. And the problems we're trying to solve here are what is the code and the configuration and all of the dependencies that were required in order for me to run my training job. This is really critically important because, as I said, development's an iterative task. And I want to be able to go back in time, and I want to be able to see how my team is doing. I want to watch my team of data scientists as they build models and see which one is actually performing the best. So what we're going to do is, on top of all of these frameworks and tools, we're going to capture all of the metrics about those training runs. You can query those. You can create reports on top of those. And I'll show an example of this a little later. What this allows you to do is find exactly the model that you want to take and then deploy. The next set of capabilities are around model management. And this is, once I have that model, how do I go and deploy it? This ranges from challenges for how do I discover the models that I have to actually deploying them. We've taken a huge bet on top of Docker, and it's been super exciting to see how this has played out, because Docker and containerization is what gives us that flexibility. We can take those models and we can deploy them up to AKS if you want to have a scale-out, large-scale Kubernetes cluster. If you just have a quick single instance service that you want to deploy, you can deploy that to Azure Container Instances. If you don't want to use our services, you can take that Docker container and you can run it somewhere else where Kubernetes runs. So you could run that on-prem in your own Kubernetes infrastructure. You could run that on top of Azure Stack. That's also what allows us to take those models and deploy them to the IoT edge devices, many of which are capable of running containers. The last thing to point out here is that the approach that we've taken integrates very, very easily within CI/CD platforms. And so you'll see ASOS talk a little bit about this, as they wanted to be able to integrate their model deployment with the rest of their software deployment lifecycle. This goes back to that point around agility and increasing the rate by which you can get those models deployed. And so with that introduction to Azure Machine Learning, I would like to welcome up Bob Strudwick. He's the CTO from ASOS, and I'm super excited to have him here. So Bob, come on up.
Hi there. Very excited to be at Build this year. Just by way of sort of background, we were here last year talking about the re-platforming of our entire consumer-facing software estate into Azure, targeting platform as a service. So we sort of know something about the business of developing sort of high availability services for the cloud. In the simplest terms, ASOS is a pure play e-commerce operator on a mission to be the world's #1 destination for fashion-loving 20-somethings. And by way of scale, we're talking sort of 2 billion of turnover, 87,000 products, 16 million active customers, 100 million page requests a second, services that scale to sort of 4,000 or 5,000 requests a second, like 1,200 people in ASOS technology, that type of scale. And you know, data science and data scientists have been part of the landscape at ASOS for maybe 3-4 years, that type of thing. And like most organizations, we sort of started in a sort of small experimental way. Now you fast forward on to now, and visual search and product recommendations and fit analytics and latterly conversational search through Facebook Messenger are all examples of the successful integration of external cognitive services and our own data science into the ASOS software stack. But I guess, you know, for us, like many other organizations that sort of aspire to be truly data-driven, there sort of comes a point where you have to try and take this beyond an activity of a data science team and aspire for this to be an activity that's embedded in every software engineering team, you know, in your crew. And so we thought we would share some thoughts about how we sort of embarked on that journey and sort of how we try to sort of demystify and productize data science as a prerequisite for the devolution of data science to all our teams. And I guess we sort of start with the idea that data science, like all other software design and build activities, can be boiled down to a very few things that you have to be very good at. And this reference architecture sort of represents, I suppose, our view of what those capabilities are at a sort of logical or conceptual level, before you get into the business of languages and machine learning frameworks and runtime environments and all of that. And here they are, model preparation, model training, model management, real-time and batch compute, and the sort of engineering wrap that allows you to take those capabilities and turn them into high availability services with security and all of that. And by creating that model of the capabilities that you need, you're sort of able to have an objective measurement of where you are and the dimensions across which you need to improve, and where technology can play a part in sort of creating a step change in where you're at. So, what was our sort of take on what were we after in pursuit of high performance data science, and where did Azure Machine Learning fit in for us? Well, I guess you sort of start with the idea that we considered that an iterative approach to data science was really an essential element of the high productivity story. Experimentation is such a critical part of a machine learning project. The simple truth is that there are no guarantees of success. You may not be able to find patterns in the data. The patterns in the data that you do find may not be strong enough to deliver the business benefit that you're after. So you sort of have to be able to fail fast. You have to be able to pivot and move on. So whilst some of this was new and challenging for us, and the creation of an iterative approach to data science is one of them. Much of what's here in the pursuit of high productivity were things that we knew something about. How to build high availability services, how to use a technology to automate build and deploy, how to use technology to automate environment provisioning. These were problems that we'd solved at scale at ASOS, and many other organizations have too. So for us, the adoption of Azure Machine Learning was as much about making sure that it didn't get in the way of capabilities that we already had. It was as much about that as it was about the introduction of new capability. So what were we sort of really after, I guess, this in two dimensions? First was the sort of normalizing of service boundaries between data science and the rest of the world. Problem statement from back then: data science capabilities legally exposed, brittle, hard to evolve. And what we were after was the establishment of formal service boundaries so that data science-backed services could just be given responsibilities to a coherent separation of companies, just like other services. That those services would have the same SLAs in terms of availability and performance and security and so on, and that we would be able to iterate the data science part of it, to go into production with an MVP of the data science, to see that bit evolve around an engineering wrap that sort of delivered that sort of rock solid technical implementation, and that would be the underpinning of this iterative approach. And that secondly, the way that you go about producing these services should be as high productivity as possible. So again, problem statement: high friction handover between different roles, limited opportunities to pair up in a way that's like routine elsewhere, limited support for data model traceability. And what we were after was an ecosystem where the frameworks that make data science highly productive could coexist with the frameworks that do the same thing for software engineering. We wanted to be able to integrate with standard CI/CD and monitoring alerting solutions. We wanted to be able to support repeatability and traceability in our experimentation, and then to support the of the successful models into production and have traceability from deployed service back to model. So that's enough background. I'm going to hand you over to Nim Kederin, who's our principal software engineer for data science, and Saul Vargas, who's one of our senior data scientists, and they're going to take you through a case study of our first Azure machine learning-based service, namely brand recommendations. So over to you guys.
Cool. Yeah. Good morning. So my name is Saul. I'm a data scientist. Here with me on the stage is Nim, a principal software engineer. As Bob was pointing out, we decided to test the capabilities that Azure Machine Learning offers and the new ways of working between the engineers and data scientists with the following proposal, which is brand recommendations. The idea is that brand recommendations for us is one of the different ways we want to help customers discover clothes in our website and in our apps by means of providing them with personalized recommendations on brands that we think our customers might be interested in, either because it's brand that it's already their favorite brands, or because it's brands that we think they don't know and they may like it. The idea is that once a customer selects one of these recommended brands, they have the freedom of going through the whole offer that ASOS has for that particular brand, which is something that for us is complementary to an experience in which we want to that we already offer, which is recommendations, personalized recommendations at the product level. One of the requirements that we had for developing this brand recommendations approach was that it could be extended or generic enough so that we could, in the future, not only do personalized brand recommendations, but also other types of recommendations of brand groupings, for instance, recommending product types, recommending colors, styles, etc. So with that idea in mind, what we decided to go as the first approach was taking a look at our already existing model for doing personalized product recommendations and just take a look at the brands of those products. To give you a more specific example, let's imagine that we have a customer who is a running enthusiast, and we already know how to do very accurate recommendations for them. In this case, we would see it's a lot of sportswear, so quite relevant, or we hope quite relevant for the customer. The idea is that we are going to run something that is logically equivalent to this. So this is like a SQL representation of the logic that we have for extracting brand recommendations out of product recommendations. If you've been paying attention to math, you will know that we didn't implement this in SQL, but in Python, and we are very happy to do it that way. The outcome will be that we get a set of recommendations, and the order is determined by the number of products that brand is represented in the recommendations. So for instance, in this particular case, our own brand, the ASOS brand, will appear first as 2 products were showing up in these personalized recommendations. It's interesting to stop a little bit and see about what's the particular algorithm that we are using for doing product recommendations and the internals of that implementation. The main idea is that we are relying on a very well-known approach for doing personalized recommendations, which is matrix factorization. In essence, matrix factorization is about coming up with vectors that represent both customers and products in such a way that by doing an operation such as the dot product between a customer vector and a product vector, you can get a prediction of the relevance for a product for a given customer. The way we implemented this particular approach before having AML as part of our toolset was the following. We had a training phase, some kind of training component that is using a lot of historical data to train the model to come up with these vectors. This is something that we are training as a batch job on a daily basis, and the current implementation relies on the Spark machine learning libraries. Then once we have that model, there is a handover to a different component, an online prediction engine. This one will do the actual computation of these dot products to recommend recommend products in real time. And in particular, for this component, the implementation that we have was implemented in the .NET framework. In order to understand why we had this particular scheme, Nim is going to give you some more information.
Thank you, Sal. So that first version of brand recommendations was implemented across 3 separate teams. And if you had a data science function in your current company that's kind of grown organically over a few years, then some of this might look familiar. We had a dedicated data science team. They would look within the business to find some data sets that were applicable to the particular proposition. In this case, that was brand recs. They would then write some data prep in Python to structure some features that they could then feed into their machine learning models. They would experiment with a few different algorithms and hyperparameter tune each one. And then the output of that team would be an algorithm selection and the hyperparameters for that algorithm. We would then give this to the big data engineering team, who would create 2 new pipelines. One pipeline which would be the data prep pipeline, which would take that code, rewrite it in Scala, and then ship it to Azure Storage. Then the second pipeline would read from Azure Storage, run the training code, and output a trained model. In this case, that was back into Azure Storage. So the output of that team is a trained model, and then that would go to one of our API engineering teams. They would rewrite the scoring logic that ran against that model to score the products. They would compose it with data from other microservices at ASOS, and then create a RESTful endpoint that we could then give to our web and apps teams. They would read that API and render the recommendations for our customers. So there's a few issues with this setup. One of the main ones is the number of rewrites that we'd have to go to for the logic that was already written by the data scientists, and the amount of coordination that it took between the teams to kind of get an end-to-end vertical slice working between all the teams. And that increased our time to market up to, it took us a few months to get a solution out. So when we began working with the new version of Azure Machine Learning, we wanted to create a team that encompassed all the roles we thought we needed to try out all the new features it had to offer. So that included the data scientists who understood the algorithms and the models. It included the big data engineers who could work with data at scale and create our pipelines. We brought in API engineers that could write scalable, performant, and reliable APIs. We also got some help from our platform engineers who could help us build our CI/CD pipelines from day one and automate everything. And with them, they brought the infrastructure and networking knowledge. We also brought in some performance test engineering help, and they helped us put scale through our systems. They brought with them the load test rigs and the large environments. And the other thing we sought to do was redefine our architectural boundary, bring in and encapsulate all of the machine logic and data science within a single team, and then we could output to the rest of the engineering teams at ASOS RESTful APIs and contractual-based messaging. The other thing we looked to do was to homogenize and standardize our tech stack. We chose Python as our language of choice. It has a wide variety of data science, it's got a great data science ecosystem. It also has fast web frameworks, and it has Python for us to do our big data pipelines. We wanted to do TDD and encouraged a testing philosophy from day one. We picked PyTest as our unit test framework of choice. And with this, as a team, data scientists and engineers working together, we managed to get a test coverage figure of around 80% on this particular solution. It wasn't a figure that was mandated. It was kind of something that evolved naturally. And with that, it gave us confidence to be able to change, optimize, and refactor our code without knowing we haven't broken the system or affected our teammates. We used application insights for our health monitoring, gave us request data, request durations, CPU, memory, networking stats, and it also gave us the ability to instrument parts of our code to find out where we're spending the time. For our cluster health, we used log analytics. We installed the OMS agent on all the nodes. That shipped container and machine metrics and logs. We used the Azure Machine Learning CLI. That helped us write our CI/CD pipelines from like day one. We could provision Kubernetes clusters. We could deploy our models and our services. And it integrated well with our ecosystem of tools that we already have at ASOS, which is in TeamCity and Octopus. So because we had an integrated team and a homogenized tech stack, we were able to shift left and get an end-to-end vertical slice up and running in a couple of weeks. We could shift left a lot of our normal development activities that are left further on down the development lifecycle. One of those was performance testing. So on our first iteration of our solution, we ran our first load test, and the results were not positive. Our response times were spiking into the seconds. And requests per second for a single machine was around 10 requests per second. Some of our larger scale systems, we normally perf test at upwards of 10,000 requests per second, so this was going to be a problem. I could deploy this into production, and I could log into the portal and then move the slider up to 1,000 machines, but I think my boss would literally kill me. So I had to find another solution. We used our code instrumentation to narrow down the bit that was taking the most time, and we located it to be the dot product. And after investigation, that dot product was running an operation in memory across a data set that was hundreds of megabytes big. So I needed to get some help. As an engineer, I could change the libraries, rewrite them to be more optimal, or change the scale. But none of those solutions would be fit for this problem. So I got some help from our data scientists on the team.
Yeah, thank you. So in order to understand what was going on, so once we located that the problem was happening when doing this dot product operation, we just needed to revisit it and reflect a little bit on what was going on. So just to recap, the idea is that in this approach, you get one vector that represents a customer in some kind of high-dimensional space, and the way you compute the relevance of the different products that are candidates to be recommended to the customer is by means of doing this dot product operation. Basically, you would get different, out of this dot product for every individual customer, you would get some kind of estimate of the relevance of the given products, and just by sorting them by most relevant to least relevant, you could come up with a selection that would be your recommendation. Now, the main problem with this thing is that this operation the complexity is linear with respect to the number of products. So, and that's not good. Basically, the moment that we have tens of thousands of products, this operation, as you can see, does not scale, and we need to do something to improve on this. Now, something that my parents told me when I was a child was that if you want to look for something in your bedroom quickly and efficiently, you need to organize it first. And this is basically what we did, but applied to the context of product vectors. The idea is that you have some product vectors, and if you want to organize them, one good way is by using a library called Annoy. There are several others. This one, what does in particular is to apply some kind of random splitting to your vector space where your products are in such a way that you end up building binary trees. In these binary trees, the leaves are the different buckets that you came up with in this random partitioning. And the idea is that products that are very similar to each other, that are close, will appear in the same leaves. Because this is a process that is done randomly, you don't always get that. So if you want to ensure that at some point any two given products that are in proximity appear in the same leaf, you basically repeat this process a number of times. Here, this parameter k, you can set it to 10, thousands, more or less it's a parameter that you need to optimize. Once you have these binary trees, you can pass from the previous linear search to a binary one. So the idea would be that you would get a customer vector, and you can just look for the branch where you would optimize this dot product operation. You do it once for every of these randomly generated binary trees, and in the end, you end up having an approximation of the top number of the top products that you would recommend to the customer. This is an approximation, so you can basically you need to sacrifice a little bit the accuracy with respect to the previous solution, but in turn you get a complexity that is much more reasonable for our case. In this case, it's something that scales logarithmically with respect to the number of products. Once we had this idea, we implemented it, we rerun the performance testing, and then we go to more acceptable numbers. In this case, we are not talking anymore about seconds of response time. We are talking about tens of milliseconds, and the number of requests per second now is an acceptable level, around 800.
Thanks, Sal. So by having an integrated team of both data scientists and engineers working together, we managed to reduce our time to market from several months to a matter of weeks. We could spend less time coordinating between teams and more time applying data science to different problems in the business. We had happier data scientists because they could see the results of their experiments in production in front of customers earlier on. And we had happier engineers because we could learn more about the data science methodology, machine learning, and from the experts in our team. So on that note, thank you for listening. I hope you found it interesting, and I'd like to hand you back to Matt Winkler.
Thank you, guys. All right, so that was a really good example of all of the problems that we're trying to solve with Azure Machine Learning applied to a very real scenario that these guys are going to be deploying into production. So now I'd like to go and switch to the what's new part. And so we've been in public preview for a little while. We launched at Ignite. We've had some things that have worked really well. We've got some opportunities to do some things better. And the things that have worked really well, as you heard in the case study that we just talked about, this notion around experimentation management, about keeping track of the experiments, giving the flexibility around the model management and deployment and the monitoring of those is super, super critical. That's really resonating well with a lot of the customers that we talk to. This next one is really important, which is around the ability for you to scale from your desktop up into the cloud. We know a lot of experiments start locally. We know that's where you're going to go and find your initial ideas before you party on the really big data set. And so that's been something, the flexibility that we've got with Azure Machine Learning has really helped customers be more productive there. This notion around deploying anywhere has also been something. We've got a lot of customers that are deploying to places not the cloud. And that's really a result of the work that we've done on top of Docker. A couple of opportunities that we've got. One is we heard feedback around how can we go and make model deployment easier. And this has been something, the feedback from all of you who have been using this, that have been sending in smiles and frowns, that's really helping us shape where we want to go and make this even easier. We got a lot of requests around taking the simplicity of the dev test loop even further for container-based deployments. Folks didn't want to deploy an entire Kubernetes cluster. They wanted to take a single container instance and be able to get something up and running. One thing that we saw a lot of people really be interested in was the ability to take the SDK and use that interactively from a notebook. The last two challenges that we've heard were about really, I love that I got all these options around compute. Can you make it a lot easier for me to create those? And so I'll be happy to kind of talk about what we're doing there. And this last one is a question that we got for anybody who's visited the booth. You've probably overheard a couple of people ask this, but it's people who know they have a challenge that they want to use machine learning for, but they don't know where to start. And so they can go out on the internet and they can kind of find, maybe they can find a tutorial. But for a lot of really common tasks, we have a ton of customers that are doing things around vision and text. We constantly got questions about how do I start solving this problem? And so those are some of the things that have gone into some of the changes that we've made and some of the things that we've announced so far at Build. So a couple of things, summary and overview of what's new. We've got in preview today the hardware-accelerated models that are powered by Project Brainwave. From this point, I'll dive deep into all of these. I'm not going to spend too much time chatting about them. We've got the Azure ML packages for vision, text, and forecasting. We've got a model gallery for Onyx models that I'm pretty excited to show what you can do with that. And then what's next? I will dive deeper into these today, not tomorrow. That's a bug on my slide. Apologies. We've got an updated SDK. Taking that feedback from wanting to be able to use the SDK from a notebook, we'll show what's going on there. Common task that we see is around hyperparameter tuning. This is something that inside the company we do at a really massive scale. And we've learned a few tricks doing that, and we're deploying those capabilities for you to use now inside of Azure Machine Learning. We're adding a couple of different compute targets, and we're making it easier for you to get those. And then we've announced a couple of different enhancements to IoT-based deployments. So for the next chunk of the talk, I'm going to walk through all of these. And so let's start off first with the packages. At Microsoft, we've got hundreds of data scientists that are working with customers. Big customers, small customers. The thing that's in common to all of them is that they come to us with really interesting problems. And as we've worked with those customers to solve those problems, we've started to see a series of patterns emerge. when you're doing vision, there's a set of very common tasks that need to happen. There's a common approach to how you go and solve those problems. And when we look out at the landscape, when we go look at a deep learning framework, we really see, we don't see those patterns, we don't see that help in those frameworks. We see, hey, here's a bag of really awesome, super performant, super scalable stuff that you can go ahead and start using, but we don't really have a great way to accelerate someone solving specific problems. And so one of the things that we've done is we've introduced packages for vision, text, and forecasting. These are three really common scenarios that we see. And what I love about these is, one, that they layer right on top of Azure Machine Learning. So that means all of the training runs that you do, you get all of that rich logging, you get all of the experiment tracking. You can deploy those through that same way. So we've already got a customer who has taken these models and deployed them to a Windows 10 device for remote field inspection. So the person walks around with this wearable device and can look at things and identify faults in those. And that's one of those things that, because we're building on top of containers, it just works. And so it's really, really great to see how quickly our customers can get up to speed on these. We're trying to take all of those steps around ingesting the data and building and training the model and give you a lot of help in accelerating that. And the last thing that's really important to point out is we're trying to compare very naturally on top of the frameworks. And what that means is you can take our defaults, and we think they'll work pretty well. They've worked pretty well for customers. The team that built the drone demo for the keynote, where it flew over and inspected the pipes, was able to turn around that pipe flaw detection model in under a day, starting from scratch, and just a lot of pictures of broken pipes. And so that's an example of the productivity with the defaults. But then if those defaults don't work for you, you can peel back the onion, you can go each layer down and have a fair amount of control over what's happening there. So this is a really great example. So on the left-hand side, you see a very basic classification sample. And so this is from Keras, which is actually a very high productivity way to go and write these models on top of other frameworks. We don't obviously have to go into the code. I know it's super small to read. That's kind of the point. But this is basically the code to do this. If you squint here, you can see I'm going over the images, and I'm trying to perform a bunch of common tasks and data manipulation on those. And this is taken straight from the Hello World image classification sample. So if we go and look at what that code looks like with the packages, you'll see here we've encapsulated all of it in a set of functions which make this a lot easier. And so you can see my favorite line is where I pull in the different ways to augment and change the data set. So I want to rotate and flip it, and I want to crop it. And so this is just this takes up 20 of the lines of code on the other side. And so this is a great way to go ahead and get started trying to solve a computer vision problem. We've got the same thing for text. We have the same thing for forecasting. If you want to get started with these today, just go to aka.ms, whack AML-packages. That'll go ahead and take you into the documentation site. It's going to tell you how to download these and get started with them. It's very, very simple to just download, and we run a couple of pip commands in order to get these packages and then start using them. And then as you want to start training and scaling up to the cloud, you'll be able to do that as well, because it just builds right on top of Azure Machine Learning. So those are the packages. The next are hardware accelerated models. And this is something that we're really, really excited about. And what this is building on a learning that we've had inside of Azure for a while, which is that FPGAs can really drive some amazing enhancements to performance. We've been using FPGAs, or field programmable gate arrays, for a while in Azure now in order to do all of our software-defined networking, in order to offload a lot of the computation for how we figure out where to route packets. What we've also learned is that they're really great for running real-time inference of machine learning models. And so this is something inside of Bing that we've been doing for a while. If anyone went to Eric Boyd's How We Do AI at Microsoft Talk on Monday, We walked through some of the use cases that we have inside of Bing. It's important to know that what this scenario of real-time scoring, which is I don't want to wait till I've got 32 images or 100 images batched up. I need to, as quickly as possible, get a result back on a single instance of data, whether that's a single picture coming from the camera, a single search query, and that's where we see these hardware-accelerated models are really, really good. And so what we've released are the Azure ML hardware-accelerated models. This is powered by the Brainwave project. If you saw Doug Berger and Ted Way's talk yesterday, they did a super deep dive on all of this. And just for kind of a reference, what we're seeing is that for the ResNet 50 model that we've got deployed, this is a really common network topology that's used for image processing, for transfer learning. We can go ahead and score a single image in about 1.8 milliseconds. And when we compare that single instance scoring time, this is orders of magnitude better than trying to do this on a CPU, as well as other ways to accelerate this. And we're providing these at a really low cost. And so we think the price performance on these is really kind of leading in the industry. Right now, we've got the ResNet 50 model. We've got more models that are coming soon. And I just want to show a little bit of code here for what this looks like. Just from a deployment perspective, this is another use case that we talked about with Jabil, which is attempting to do analysis of circuit board images to find flaws. So what they do is they build and train a model with Azure Machine Learning. They use the ResNet hardware accelerated model in order to go and extract out a ton of interesting features of those images, and then they take the last layer off, and then they hand that into their own classifier to say, is this broken or not? This is the manufacturing equivalent of hot dog or not. And then we go ahead and deploy that onto the FPGAs to accelerate that ResNet 50 portion. So let's look at what this looks like in code. And so what I've got here, this is just taking the notebook that's provided in the project, running it in Azure Notebooks. This is hooked up to my Azure Machine Learning account. You have to fill out a survey request in order to get access to these. Because we're in a preview stage with these right now. We want to make sure we get these to folks who are going to use them. So you have to request access to this. And then the part that I want to show here is first where I pull in the ResNet model itself. So you'll pull it in from the AML real-time AI package. Let me make that a little bigger so folks can see it. And then what's interesting here is you go ahead and define a pipeline of the different transforms that you want to have happen. Because what we often see in these scenarios is that there's part of this that's going to be accelerated by the FPGA. There's some of that's going to get executed on CPU. And that's part of what we're pulling together here. And so you'll see I pull in 3 different stages of my pipeline in order to get the data. For this stage right here, which is what's taking the bulk of the time, I'm pulling in that model, the ResNet 50 model. This is where in the future you'll be able to point other model types here. And then I just go and deploy the service. And this takes under a minute to go ahead and deploy the service to get that out there. And then the other thing that we'll do is we actually go ahead and create a client for you. So you can test that right away. The protocol format is gRPC, so you can take any client of that to get super, super low latency from your application. And then you can just go ahead and make the calls to that here. So here we're saying score image. This will then go ahead and return. In this case, in the example here, we built a classifier on is it a snow leopard or not. And so that's really easy to get started with. So go ahead and go. There's a much easier URL, which is aka.ms/aml-real-time-ai. This will take you into that GitHub repo. You can start playing with all the code today, and you can go ahead and fill out that survey. Last thing that I want to talk about is the Onyx model gallery. And this is something where we see people want to be able to use models that have already been built. It's incredibly expensive and time-consuming to build a lot of these models, and other folks have taken on that time and expense for you. And we want to make sure that those are very easy to consume into your applications. And so if you go to gallery.azure.ai, and I'll flip out of here now, you'll see we've got a set of models for doing kind of the hello world, MNIST, digit recognition. We've got YOLO v2. I think we're working on a YOLO v3 impl. This is you only look once from the Clever acronym division. But this powers some really nice object detection capabilities. We've got a collection of other interesting models here that are all ONNX models that you can easily download. Why is ONNX really, really important? Well, this is a common interchange format for these models. And so what you can do is you can download one of these models, and if you're building a Windows application, you can use WinML in order to just drag and drop the model into Visual Studio and then be able to run the model inside of your app. This is something that was shown in the keynote yesterday morning, but you can take any of these and just pull them right into your app. The other thing that you can do is very easily take these and then deploy these as services. So if you want to deploy an object detection service, all you have to do is download this, and then we'll flip over here. This is another notebook that's running, and this is on top of the model management capabilities. The first thing that I need to do is just write a score.py function. And you'll see here what I do in this. I have two methods here, init and run. Init is as the container spins up. This is where I do any pre-work that I have to do. Run is the actual invocation of the service itself. And so with just a little bit of code here, you'll see that I load up the model, and then I go and invoke that. And here we're using the Microsoft Cognitive Toolkit in order to provide our ONNX runtime. You could also use NVIDIA's TensorRT. You could use MXNet. There's a few different implementations of this. But once I have this, all I need to do is then deploy. And so now I'm sneaking ahead a little bit and showing some of the SDK. But here what I'm doing is I'm going to deploy this to an Azure Container instance. So I define, hey, I just want this to use 1 core and a gigabyte of RAM. I'm just playing around with this. I just want to try it out. I specify the model that I want to deploy, a little bit of the runtime and the dependencies to pull in, and then I'll go ahead and deploy this. And so this will take about 3 or 4 minutes right now. We want to go make that faster. But in 3 or 4 minutes, you'll have an endpoint that's up and running that will enable you to go and score against this model. What's cool about this is you've skipped the build and train step. Someone else has already done that for you. You've just taken this and you've now deployed this model. And so again, that's gallery.azure.ai/models will take you right there. I'll put a plugin for the gallery. There's a ton of sample projects there, some real-world scenarios that are deployed there. A lot of those are based on customer engagements that we've had. So if you want to build a recommendation engine, you can go find a solution. If you want to do anomaly detection on top of IoT workloads, there's a solution there. So definitely go ahead and check that out. Most of those, you can get all of the source code and a lot of the data that was used to train the model. So they provide a really great starting place. So now let's talk about the SDK. And this is something that you have asked us for, which is give us a really easy way to put this into notebooks and be able to use this. And so there's some really nice capabilities on this. You can install this anywhere you can run Python, basically. So you can install on top of 2.7 or 3.5 plus. It'll run in a Python IDE or in a notebook. And there's a couple of things that we're trying to do here. One is we're trying to make it really easy to provision compute targets. I'll show how to do that on the next slide. We want to make it very easy to run those training jobs local to the notebook or dispatch those to go run on a large-scale cluster like Batch AI. One of the really neat features that we're adding here is some hyperparameter tuning capabilities that are based on things that we've done internally. And then all of those things that I talked about being able to do with the service, being able to find your run history, being able to query that, being able to deploy the models, all of that can take place from the SDK. And so let me just go and show what the hello world for this looks like. And so again, here I'm in Azure Notebooks. the nice thing is this runs anywhere you can run Python. I'll show my other favorite super cool place to run this in just a second. I've got a very basic machine learning model that I'm building out of one of the data sets inside of scikit-learn. And what I want to do here is I'm going to actually do a little bit of sweeping of the parameter space. I want to find the different, the value for the learning rate that's going to help me find the best performing model. And what you'll see here is I'm actually doing a set of runs. And so I'm saying that I'm going to start the run, and then the rest of this code just looks like exactly what you'd get if you went to any of the books on, hey, this is how to use scikit-learn. There's one thing that we're doing special here, which is that we're logging out a set of interesting metrics. Remember when I said what the experimentation capabilities do is the ability to keep track of all of those metrics? This is where you say, these are the things that are interesting to me. And so here I'm saying, hey, what were the columns? What was the mean squared error? And what was that value of alpha? This is important because then later I can come and query that. And so I enumerate over those, and then I say that the run is done. So I went over 19 different parameter options. And then what you'll see here is I can actually go and say, hey, for that run, give me all of those child runs that occurred. And let me load up all of the metrics for those runs. And then if you just look here, what I'm saying is, hey, can you please find for me the run that had the lowest mean square error? Right? And I can pick different metrics. What's flexible about this is you can pick the metrics that you care about, whether that's an F1 score. It's really up to you. And so I'm just running a query here, and I'm saying, hey, give me the best one. And this is when it used this value of alpha. If you don't want to do this programmatically, if you'd like to visualize this, this is just data. So I can go ahead and pull all of those run metrics in, and I can plot those. And you'll see here, yep, right about there is where I found the lowest value, which is the value that I'm trying to optimize for here. And so this gives you a very flexible way to just treat all of your runs just as data, right? And so then any other tricks that you know to apply on data, plotting these to visualize them, putting them into other selection criteria, programmatically selecting one, you can go ahead and do that. So now, let's go ahead and find that best model. We're going to promote that one, which says, hey, this is a model that I want to publish. And then we've now got to just define, how do I want to score that model? And so you'll see here, this is very similar to what I showed on the previous slide about the ONNX model gallery. I just write a simple Python file. What's nice about this is that it's just Python. So if you have a custom logging library, if you want to call out to Cosmos DB in order to go get some cached values, you can go ahead and write that here. So it's not a black box. It's simply a Python file within a init and a run. And so that gives you a very flexible way to control the data that comes in and the data that comes out. And so you'll see here, in my init, I load that model. I run the prediction here. And then I just return the result as JSON. If you don't like JSON, that's totally OK. You can return it as something else as well. You can also author an environment configuration file. It's just a YAML file that specifies a bunch of dependencies, which again, here, now this is the same code that I showed before. Again, here is the compute definition. I can go ahead and deploy this. And we've still got a bunch of perf work to go do, so this will get faster, which is why I'm not clicking through all of these in real time. And then at the end of this, again, we generate a nice client for you, and so I can go ahead and do this, and you'll see I'm actually scoring an example right here. The other thing that's nice about this is I can get the scoring URI, so then I can take this and put this into my application. The other thing is, if you replace score with swagger.json, we'll actually return the Swagger definition for the service. Why is this really important? There's a whole tool chain that will be able to generate interesting clients in C# and Ruby and Go and Swift and whatever else you care about from that Swagger definition. So this makes it very easy to go and consume the service from just about anywhere. So the other thing that I want to show here, there's still a couple of setup pieces that don't quite work, so I can't show it in real time. This will run anywhere Python runs. So that means inside the Azure, you can go ahead and open up an instance of Cloud Shell, which gives you a bunch of compute right in the Azure portal, and you can actually install this SDK and start using it. So you actually need to have nothing on your machine. You can browse to the Azure portal. You don't need to deploy another VM. And you can actually start doing everything that I just showed directly from Cloud Shell. We don't think a lot of people are going to do that, but I think it's a super cool example of why this is really important, because we're giving you this compute environment to go ahead and use. OK, we've added support for Azure Container Instance and Batch AI. AKS will be, the Kubernetes service will be lighting up in just a little bit of time. Currently, we're on top of Azure Container Service right now. As that migrates to AKS, so are we. I just want to show real quick 2 code snippets here. This first one is about creating a Batch AI cluster. And what this allows me to do is specify, hey, I'd like to create a Batch AI cluster. I want it to auto-scale. I'd like it to start with 1 node so that I don't have to pay a whole lot. But then I'd like it to go up to 2. This one's really simple. It could go up to 2 nodes. If you want to do this to 200 nodes, it's very easy to do. The other thing that you can specify here is if you want a priority cluster. What that means is that the VMs aren't guaranteed to live. But the bonus to you is that they cost about 80% less. And so you can specify that. We'll see a lot of customers who are very interested in doing that for kind of large-scale nightly batch jobs. They'll try it on the low priority compute, and if their job doesn't get done, then they'll go ahead and deploy it and pay full price. But that's a really nice way you can kind of optimize your spend. And then I've shown the Azure Container Instance a couple of times now, so I'm not going to dive into that sample. So let's talk about hyperparameter tuning. And this is something Saul talked about from ASOS, which is as part of the task, you want to explore the space. You want to find the right combination and configuration that will produce the right model. And so this is something inside the SDK. We've got an API that's called Hyperdrive. You can see that right up here. And what this allows you to do is define, these are the parameters that I want to do a search on top of. I can define how I want to do that search. I can do a grid-based search. I can do a random search. And then what's really interesting about this is we have an early termination policy. This is incredibly important as you start doing hyperparameter tuning scale because you don't want to waste compute. And so if you can detect early on that the model that you're building is not going to be one of the best ones, you can go ahead and terminate that run. This is something that the Bing team, this exact technology is used by the Bing team, it's used by the speech team, and a number of teams internally. And what we've seen, and you can kind of just see on this graph here, very, very kind of simple, but there's a set of these runs, like this green one and this orange one and this red one, that all got killed early. And while this may not seem like much for something that's only got 5 or 6 runs, what we've seen when we run this at scale is that we can typically reduce the amount of compute consumed by about 50%. And so that gives you a much more efficient utilization of all of your hardware, and it helps you find the best model, and you can explore a much larger space for the same cost as a more naive hyperparameter tuning approach. So next thing to talk about, IoT deployments. At Connect, we unveiled the capability to take Azure Machine Learning trained models, deploy those to IoT devices. One big thing to talk about here is that in partnership with Qualcomm, we announced a developer kit. And so what this is a really cool camera with some hardware acceleration on it that you can build and deploy models for it with Azure Machine Learning. We see this, the number of vision scenarios that we see our customers coming and talking to us about, it's almost every conversation we're having. And so what this gives you is a very nice way to target the Qualcomm hardware, which is going to be running in lots and lots of places, and Azure Machine Learning is the way to go and build and deploy those models. You can sign up for early access to the dev kit today. Other than that, we haven't made any significant changes to our IoT deployment story. But if you're interested in that, you can go to the AI toolkit for the IoT Edge. This is a set of sample projects and everything that you need to go ahead and get started. This is something we've got a number of customers that are running. It's not just, sometimes when I hear IoT, you think things and you think tractors, but we also see a number of interesting implications in retail or places where you want to deploy. The edge isn't just a sensor, it can look like a computer. And so we see a lot of times where you want to deploy somewhere that doesn't have a full IT infrastructure there, and you can very easily target deploying the models there to process register receipts, to process information that's coming in from cameras, and those such things. So we are on the home stretch with about 10 minutes to go. What's going to happen next? So there's a couple of other things in addition to those features that we're doing. We're going to be rolling out globally. I think we're up to more than 50 regions worldwide. And so that's going to be something we're going to continue to deploy across those regions. Soon we'll be bringing the services to general availability. We're adding in all of those features that I just showed before we get to GA. So what should you do now? Right now, you can try out the hardware-accelerated models, fill out the survey form. You can try out the AML packages. Those are available today for vision, text, and forecasting. You can go and use the Onyx Model Gallery. If you find any of those interesting models that you want to take, deploy those into a Windows application or deploy them as a service. The capabilities that I showed after that, so all of the SDK functionality, we're currently in a private preview on that. And so we've created an insiders program. So if you go fill out this form at aka.ms/AzureML Insiders, it's a brief survey. That's what we're using to bring folks into the private preview to start using these. The thing that we ask in return for giving you access to the bits is your feedback. As you can see, the changes that we're making are directly in response to customers like you. And so that feedback is super, super critical to the team. So if you want to get started with Azure ML, just go ahead and go to azure.com/AI. This is the entry point to all of those interesting AI capabilities that we have. Check out the gallery, and if you're interested in the camera, go ahead and sign up for the dev kit. And so with that, I am very, very grateful, and thank you very much to the folks from ASOS who were here. Very much appreciate having you here and talking about your story. I'd like to thank all of you again for coming. We'll be around afterwards for questions, so if you have any, just come on up. And thank you very, very much, and have a fantastic rest of Build.